तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. Last time I had introduced the ideas of inductance and how inductance connects up to magnetic stored energy. I am going to go more into detail on it this time, and I am going to introduce some mathematical tools that make such calculations much easier. So, let us see what we came up with last time. We did not fully prove it because we did not have the mathematical tools to do it. What we said was that you have two equations, curl of B equals mu naught J, and you have curl of E is equal to minus del B del T. This was the new rule, that earlier we had curl of E equals 0. Because of Faraday's law, we now know that curl of E is equal to minus del B del T. So, we said supposing there is a current J which is distributed through space. This current through Amperes law produces a magnetic field B. But this current must have come from somewhere. It does not just appear in one instant. So, let us assume that J of R grew in a uniform way, that is, at every point it grew continuously. So, we defined a new current J of R t, which was the same J of R. I will call it J naught of R and B naught of R. This J naught of R times a function alpha of t, and the alpha I chose was starting from t equals 0 to some capital T, just linearly increased to unity. So, when alpha is 1, J is J naught, when alpha is 0, J is 0. So, I am very slowly turning on this current. But if you look at Amperes law and I substitute this formula into it, what do I get? I get curl of B is equal to alpha of t times mu naught J naught, because that is what I have defined J to be. Now, let me guess. I will guess that my B of R t is some other function f of t B naught of R. Substituting in there, what do I get? I get f of t curl of B naught is equal to alpha of t mu naught J naught. But I already know that this is true. Curl of B is equal to mu naught J naught, because that is the original equation that gave me B naught out of this current distribution J naught. So, I can cancel these out. So, I get f of t is equal to alpha of t, which means that my magnetic field B of R t due to this current is also equal to alpha of t B naught of R. Now, why is this important? It is important because we can now start looking at Faraday's law. Now, if we look at Faraday's law and we say I want to know what is happening to energy input into the field. So, the energy in the field is volume integral J dot E d cubed r with a minus sign. J dot E is the energy dissipated. So, minus J dot E is the energy injected. So, J dot E has to be worked out, but I have curl of E is equal to del B del T, and that J is equal to curl of B. All these facts I have. So, let us see where we can get using this. What I do is I take the loop integral form of this expression. So, what does that mean? If I take the surface integral on both sides and you apply Stokes' theorem, I get loop integral over some curve C of E dot dl is equal to minus d dt of surface integral B dot ds. So, if I now want to say what is J dot E, I need to understand what happens if I dot this E and dot on the other side as well. But J is already connected to B. So, the particular J I am using is nothing but alpha J naught, and the particular E I have is coming out of here, and let us see what that E gives me. I have chosen that alpha of t is equal to some t over capital T, because it goes from 0 to 1. This is alpha. Since this is alpha, d dt or del del t is equal to the time derivative of alpha, which is 1 over capital T times B naught. Why? Because we already have that B is alpha of t B naught of r, and if I take the time derivative, it can act only on alpha. So, I get B naught of t is equal to 1 over t, B of t partial derivative with respect to t is 1 over capital T B naught. So, my Faraday's law says curl of E is equal to minus 1 over capital T B naught. And I also have my Amperes law, which says that curl of B is mu naught J naught. It is these two terms that I use to get where I want to get, which is what I had talked about last time, and I motivated that you can basically add energy into the field talking about J dot E. The reason is, as I inject current, as I inject increasing amount of current, my magnetic field increases. As my magnetic field increases, I induce an electric field. That electric field dot J means I am doing work, and therefore, I can take this entire picture and make it into a statement about work done to increase magnetic field. For now, let us look at the result I put down, which is the stored energy was equal to B squared over 2 mu. Now, I am going to derive the same thing for an inductor. We have already done it once, but I think Faraday's law is one place where revision is the only way of learning things. So, what what I am going to do is to recover the circuit theory picture of inductance. Let us say I have a solenoid. I have n turns and this solenoid has a length capital L. Therefore, my turns per length little n is equal to capital N over capital L is equal to turns per meter. Now, if I inject a current, I know that the magnetic field B is in the z direction and is equal to mu times the number of turns per unit length times the current. The flux phi m, phi magnetic, is equal to the surface integral of this B over a cross sectional area. So, it is equal to mu n I times area. Now, I know that the amount of voltage that is dropped V is equal to n times the per turn EMF. Induced. Now, this is not quite correct, there should be a minus sign. So, what I mean is that if there is a magnetic field increase inside the coil, there is going to be an induced EMF. This voltage is the voltage required to overcome that induced EMF. That is why there is no minus sign here. So, how much is it? It is equal to n times this piece mu n A times d dt. Okay. So, I have taken a minus sign which is really what should be there and I have removed it. So, I have got a plus mu n times mu n A d I dt. So, let me explain that sign again. If I have a loop and I have a strengthening magnetic field, B is increasing because the current I is increasing. Now, if the current is increasing and therefore, the B is increasing, what is happening is an EMF is developed. What is the direction of that EMF? The direction of the EMF is so that a negative B will be produced. So, the EMF is trying to drive a current in the opposite direction. So, the EMF induced is in opposite direction. So, it is like a resistance, it tries to prevent this current from increasing. How does it try to prevent it? It is trying to put a voltage that is trying to drive current in the opposite direction. So, if you still want to impose this increasing I, what you have to do is you have to apply an equal voltage in the direction of the current. So, it is as if for every turn there is a little. So, this is my applied voltage. For every turn there is a little battery, induced battery, that is trying to resist my applied battery. This induced battery is proportional to d I dt. If there is no change in magnetic field, there is no induced EMF, and magnetic field increases only if current increases. Therefore, I need to apply a voltage that is proportional to d I dt or proportional to d phi dt. So, this voltage is therefore in the plus direction. It is in the plus direction because I have to overcome a minus voltage. So really I should have a minus sign here, indicating that V is n times the negative of the per turn induced EMF. So overall a positive sign results. But this is nothing more than inductance. So this is not saying just V equals L di dt. Now we know what stored energy is in this system, because we know that if you want amount of energy put into the device, is equal to integral from 0 to t of I of t V of t dt. It is the amount of current in the direction of the applied voltage integrated over time. But my V of t is already I of t times L di of t dt times dt. Assuming L is a constant, I can pull it out. This gives me this kind of relation, which is integral 0 to t d dt of 1/2 I of t squared dt. And this of course is a total derivative integrating from 0 to t. So that tells me that stored energy I should say change in is equal to L times I of t squared over 2 minus I of 0 squared over 2. So, it is nothing more than the inductance formula, and of course, it has to be. The inductance came from here, but let us see what went into it from the point of view of magnetism. What went into it is that you had a strengthening magnetic field because you are trying to drive more current. This strengthening magnetic field, due to Faraday's law, is trying to apply an EMF in the opposite direction. That is, it is trying to drive current in the opposite direction, therefore resisting the increase. This voltage applied in the opposite direction is therefore having work done on it by the forced current. You are driving a current through the system and the system is resisting. It's like you are pushing a rock up a mountain, and therefore you are doing work on the system, and that work is clearly equal to this amount. Now the question is, where is this energy going? We know one thing. We know that if you now reduce that current, supposing you took this current and you gave it a reverse direction and brought it back to 0. In this period, we know we have got this. In this period, so this is 0, this is some time t, this is some time tau. In the second period, what you have is change in stored energy is equal to L times I of tau squared over 2 minus I of t squared over 2. I can add these two up. Because it was a total derivative, this term will cancel out. The I of t term will cancel out. Here it is plus, here it is minus. So, total change is equal to L times I of tau squared over 2 minus I of 0 squared over 2. What that means is, I took the current, let us say starting from 0 current, so I of 0 was 0, I took it to 10 amps, so some energy went into this device, I brought it back to 0, that energy came right back. The total change in energy was 0, because I of tau is equal to I of 0. This is not a dissipative device. Whatever energy I put in came right back to me. So, energy is getting stored somewhere. This energy cannot be stored in the coils, because it is not, there is no storage in a resistor, for example. It can't really be stored in electric fields, because supposing I had a situation like this. Supposing for a while the current was constant. If the current was constant, then I know that my magnetic field was constant, electric field was 0, because curl of E was equal to dB dt. If dB dt is 0, electric field is 0. So, I have electric field, let us say negative, electric field positive, electric field 0. Negative positive is only in the sense that it resists the increase, it resists the decrease. So, here it is trying to slow things down, here it is trying to speed things up, but in the middle there is no electric field at all. If there is no electric field, energy cannot be stored in the electric field. So, where can it be stored? Well, there is only one culprit. The culprit is the magnetic field, because it can't be stored in current, since the current by itself you do not see storage in a resistor. So, it must be some, it is certainly related to the current, but it is some special feature of the current, and the special feature we can think of is that the current induces a magnetic field. Now, how much is that energy? Well, we know it is Li squared. So, we know stored energy is equal to Li squared, but now what is L? We have got L from earlier, it is equal to mu n times n I squared over 2. Well, I can write this as mu n squared L I squared over 2. Now, the magnetic field is equal to mu n I. So, I can see an I squared there, I can see an n squared there, but I can only see one mu. So, I can write this as mu n I whole squared times L divided by 2 mu, and of course, there is an area also times A. This mu n I squared is B. So, it is equal to B squared times volume divided by 2 mu, and that is where we get back the same formula, that energy in the magnetic field is related to B squared over 2 mu. It is the same idea. The idea here we will come back to in mathematical terms, but the idea here is straightforward. It is that we have a known device where we have known magnetic field. In order to increase the magnetic field, we found we had to do work. The work we had to do, the total work we had to do to bring a current up from I of 0 to I of t was 1/2 L times I of t squared minus I of 0 squared. We know that this is a conservative kind of change in energy, because if I bring the current back down to 0, I get all the energy back. It is not a resistor in any way. If this were a resistor, if I brought the current back to 0, I would have dissipated an equal amount of extra energy. I would not have got any energy back. It is more like a capacitor. Whatever energy went into the device came back when I gave it out, when I brought the current back to 0. But I can write this term down in terms of what I know about the magnetic field. So, I know that L is nothing but mu n times capital N times A. So, I have written that down, I squared over 2, but mu n I is B. So, I can write this expression in terms of magnetic field, and what do I get? I get magnetic field squared times volume divided by 2 mu. So, again B squared by 2 mu is energy density in the B field. Now, at the end of last class, I introduced the concept of mutual inductance, and let me repeat that so that you feel more comfortable with it. Supposing I have a coil, and supposing I am driving a current I in it. I have another coil, and that coil does not have to be along the same axis, and it does not have to point in the same way. And let us say that that coil is carrying a current I, this is I1, this is I2. The total magnetic field at every point is due to the magnetic field in I1 and due to the magnetic field in I2, due to I2. So, the magnetic field B is equal to sum on 1 2, okay, I equals 1 2 of mu naught over 4 pi volume integral J sub I cross gradient of 1 over R12 with a minus sign d cubed R, or if you like J cross R12 over R cubed. So, this is the Biot-Savart law, and from the Biot-Savart law you can see that if I have two different currents, the magnetic field is just the sum of those two currents. So, the magnetic field here is, or rather if I take the surface integral B dot ds, so this is the total magnetic flux, it is going to be equal to sum I equals 1 2 mu naught over 4 pi integral over the surface of this quantity. So, there is a volume integral to give me the magnetic field and a surface integral to give me the magnetic flux. So, it is a very complicated integral, 5 different dimensions. However, it is linear in J. So, if I made J equal to twice its old value, the answer just doubles. It does not matter how many times I integrate over space, still it is linear in J. Since it is linear in J, I can, supposing I know that I have fixed currents I1 and I2, all the shape of that coil goes into this integral, but I can write this J in terms of some complicated function. So, I can write it as sum I equals 1 comma 2 I sub I times complicated stuff which depends on I. As long as the coil shape does not change, this bracket does not change, because it depends only on how the coil goes around in space and how that coil goes around in space. The amplitude of the current comes through II. This is the result for unit current, this is the result for changing that unit current into its actual value. which means I can write this whole thing as a coefficient, it is a number. So, I write this as some I equals 1 2 of some C I I. Now, these numbers are not easy to calculate. As you can see, I have to do a lot of work, lot of integrations to get that number, but I can put J, the current, as 1 amp, calculate this expression, that gives me the constant C. Then I put the actual current, which is 10 amps, through II, and the product of those two gives me the correct magnetic flux. I can generalize this for n coils. So, what I get is phi through coil sub I is equal to sum on J equals 1 to capital N, some coefficients, and here I will use the symbol that is usually used, Mij times the current in coil J. It is the same idea, that constant multiplies the current in the jth coil. So, this Mij, what would it be? It would be mu naught over 4 pi integral over the surface coil 1 or coil I, okay. Then this current, there is going to be a volume integral. Now, that volume integral also reduces to a loop integral because there is no current anywhere else. So, it will be another a loop integral over coil 2 or coil J, then there is unity current. So, that J does not matter, but there is a dl cross R12 over R12 cubed, and then dot ds. That is what it is. So, you can see it does not depend on current at all, but it depends in a very complicated way on the shape of the coils. This is over the surface of the coil, this is over the loop of the coil. Now, you can make this into 2 loops, that is not difficult, it is just a matter of doing vector algebra. But for our purpose, what is important is this whole thing is a constant, which depends on I and it depends on J. So, that is why I have written it as Mij. So, it is therefore a matrix equation, and as I wrote down last time, that matrix equation can be written as the flux in coil 1, flux linking coil 2 up to the flux linking coil n is equal to a matrix M11, M12, M1n, M21, M22, M2n up to M n1 up to M n n. It is a matrix, and multiplying this matrix is I1, I2 up to In. So, this is just a linear algebra problem now. If I know these coefficients, and usually the middle ones are called Li11, L22, etc., because they represent the amount of flux linking a coil due to its own current. So, that is what is called self inductance. These terms are all called mutual inductances. But if I know these numbers, then calculating flux is just matrix multiplication with currents, calculating currents is just inversion, given flux is just inversion. I can just take the inverse of this matrix multiplied by the fluxes gives me currents. It is also easily provable that this matrix is always invertible. They are physical things, therefore, you cannot have a non-invertible mutual inductance matrix. Now, let us take the time derivative of this. if we take the time derivative of this, then we know that d phi I dt, which is the rate of change of the flux in coil I, that is equal to minus loop integral E dot dl, because of Faraday's law. Curl of E is equal to minus del B del T, integrate over the surface, you get loop integral E dot dl is equal to minus d phi dt. But phi I has a representation, so you can say d dt of sum on j equals 1 to capital N m I j I sub j is equal to minus loop integral E dot dl on loop C I. So, on the ith loop that you have to do this loop integral. Now, let us assume that these coils are stationary, moving coils will come to later. So, then this d dt does not affect capital M, it affects only capital I. So, you get sum j equals 1 to capital N m I j d I j dt is equal to, now what is the loop integral of E dot dl over C I? It is nothing but the induced EMF. So, it is equal to V sub I. The minus sign is absorbed because, as you remember, this is the resistance that the loop offers to driving a current. Therefore, the applied voltage required is minus of this. So, the minus sign gets absorbed. Now, this is nothing but a generalization of what we have already done, because we already have L I d capital I dt is equal to V I. That is our self inductance equation. This is a general equation. If I have multiple coils and all the coils have varying currents, then the total induced EMF is nothing but the sum on all the mutual inductances times the time rate of change in the other coil. You add them all up, that gives you the induced, that gives you the applied voltage required to drive your current in your coil. So, now from this we can also work out energy, it is a trivial thing, and you can work out what the stored energy is. I will leave it as a exercise for you to try out, and once you have struggled with it a little bit, maybe I will derive it in the next lecture or two. I want to do one other thing which will set the context for doing the work in the next few lectures. We can see that once we have curls, we are running into trouble with the vector algebra. I can always quote to you a result, but it is not obvious when I write curl of E cross H, you won't know what it is. It is difficult to understand where terms like this are coming from, how many terms they correspond to. So, we need a little bit of mathematical machinery which makes all of this rather simple, and this machinery has now become very sophisticated, and I am going to introduce the simplest parts of it, which allow you not to remember any of the formulas in your book, and that is quite important. I mean, if you have to keep memorizing all the formulas, you don't learn the concepts. Whereas, if you learn the concepts and can just work out in a couple of minutes any formula you need, the formulas are anyway there in the back of any book. So, you can you come out of the course learning a lot more. The basic thing we need is to understand how to represent curl or even cross product. As you know, what we do is we write determinant of a matrix x hat, y hat, z hat, ax, ay, az, bx, by, bz. And then we have a standard way of writing down what determinant is. But let us look at what determinant really is. It says take every possible combination of an element from the first row, from the second row, from the third row, such that you do not repeat the row and you do not repeat the column. And when you do that, make sure that you always go in the 1, 2, 3 direction. If you have to go in the 1, 3, 2 direction, that is you have to go in the other direction, then put a minus sign. Let us see if this is true in the way we do it. For example, we say x hat ay bz minus x hat az by. So, we took the first row first column, second row second column, third row third column, went 1, 2, 3, so plus sign. Then we went x hat az by, so we went 1, 3, 2, so I put a minus sign. What about the next one? Y hat az bx minus y hat ax by. What did we do? We had y hat, so we have taken up the second column and the first row. Then we did az bx and an ax bz. We can't do az ax because that is not using the third row, we are doubly using the second row. We can't do az bz because that is doubly using the third column. So, they are the only two choices, y az bx, y ax bz. Now, if you look at this, it is 2, 3, 1. All these three numbers 1, 2, 3, 2, 3, 1, 3, 1, 2, they are all going in the cyclic direction. So, if I wrote in a circle 1, 2, 3, 1, 2, 3 goes this way, 2, 3, 1 goes this way, 3, 1, 2 goes this way. All of them go in the same direction. So, they are all given the positive sign, whereas 1, 3, 2 has to go the opposite direction, and therefore, I give it a minus sign. Similarly, 2, 1, 3, similarly 3, 2, 1. You can check it for yourself. 2, 1, 3 for example goes this way, 3, 2, 1 goes this way. So, it is just a matter of how you go through the numbers 1, 2 and 3, and that is what gives you the signs. Now, there is a symbol which represents all of this. Specifically, it is called epsilon ijk. It is called the unit antisymmetric tensor. It is a big name for something very simple. It is equal to 0 if any two indices are repeated. So, if you have 1, 2, 2 or 2, 3, 3, then it is 0. They have to be different indices for it to be non-zero. It is equal to 1 if cyclic. It is equal to minus 1 if anticyclic. Now, if you had this epsilon ijk, then clearly the determinant is nothing but determinant of A cross B is nothing but sum on j k I, okay, E sub I unit vector times this epsilon I j k A j B k, because if you look at it, you are using E sub I, A sub j, B sub k, and depending on whether you go clockwise or you go counterclockwise, you put a plus sign or a minus sign, and that is taken care of by the epsilon I j k. Now, this sum actually goes through a lot of cases we do not care about. For example, I equals j equals k equals 1, we do not want that, but that is where epsilon I j k is equal to 0. So, this is a shorthand way of defining cross product. Does not look short, but it is. We also suppress this sum. It is assumed that if I appears twice, it is summed over, if j appears twice, it is summed over, and if k appears twice, it is summed over. So, we write A cross B is equal to epsilon I j k unit vector along I, jth component of A, kth component of B. What happens with curl? Curl of B is the same thing. It is epsilon I j k unit vector along I, derivative along j of the kth vector, because it is after all just the matrix. Okay. So far so good, but now there is something new. This epsilon I j k has a lot of symmetry properties, and because of its symmetry properties, you can simplify a lot of expressions. But before I do that, let me also introduce some other things. First of all, how do I represent divergence? And how do I represent a vector itself? Well, a vector A is equal to x hat A x plus y hat A y plus z hat A z. So, I represent in the same notation by saying E sub I A sub I, meaning E1 along the first direction times the component along the first direction, second unit vector times component in the second direction, plus third unit vector times component in the third direction. So, this is my vector. And what is divergence? Divergence of A is equal to del A x del x plus del A y del y plus del A z del z. Well, it is equal to, if you want to write it out, it is equal to E I del del x I dot producted with E j A j. That is, this is the gradient operator, this is the vector, and if you take the gradient operator and dot product it with the vector, it gives you this result. So, what is it equal to? It is equal to del A I del x I, because E I dot E j is 0 unless I is equal to j. So, again I appears twice, so summed over. Similarly, here I appears twice, summed over. What about gradient of a scalar? Well, gradient of phi, it is equal to del phi del x along x plus del phi del y along y plus del phi del z along z. I will use this form, which is E sub I times del phi del xi. This is my vector component in the ith direction. So, this is gradient, again I, so I is summed over. This is usually called Einstein notation. It is because when Einstein introduced relativity, the mathematics became so complicated he had to invent shortcuts. But he did much more complicated things, and we are going to do very simple things. But nonetheless, this notation is very useful. It is very useful because it is very compact, and it turns out there are a lot of things you can do, and you can see a lot of simplifications which you can't see if you are going to write out everything in great detail. Now, let us see if we can derive some of our older results. We said that curl of gradient phi is 0. We did that by showing that you have two identical rows, and therefore, second partial derivatives are continuous. It went to 0. But can we do it in using our new notation? Well, what does this become? This becomes epsilon I j k E sub I del del x j of gradient phi in the kth direction. That is coming out of the definition of curl. Definition of curl is epsilon I j k unit vector along I del del x j vector along k. So, unit vector along I del del x j vector along k. But this vector along k is actually del phi del x k, because that is what gradient is. So, now you have this expression, you have these two derivatives. So, you can write it as E sub I, well, you can write the epsilon I j k out, E sub I del squared del x I del x j acting on phi. Now, if I and j are equal, epsilon I j k is 0. If I and j are not equal, we know that, sorry, j and k. We know that when j and k are not equal, you can have I j k or I k j. That is, you can go through your you can go through your 1, 2, 3 cycle. Let us say this is E1 and this is del del x2, this is del del x3. You can either go through it this way or you can go through it this way. And when you go through it this way, you get a plus 1. When you go through it this way, you get a minus 1. And therefore, this term combined with this epsilon I j k automatically gives you a 0. The antisymmetric properties of epsilon immediately tell you curl of gradient of phi is 0. What about divergence of curl? Well, what is divergence? Divergence is del del x I of curl of A component along I. So, put that down, del del x I times epsilon, the ith component is epsilon I j k del del x j A sub k. Why? Because if you go back here, this is the definition of curl. Now, if I want the ith component, it is whatever is multiplying E I. So, I remove the E I and the rest of it is epsilon is the ith component, which is what I have written, epsilon I j k del del x j A k. So, I can write it out again, epsilon I j k del squared del x I del x j of ak. Almost the same thing, but not quite. I have my first two indices rather than my last two indices, but epsilon does not care. Epsilon does not like any of its two indices to be the same. So, I and j cannot be equal, and if you interchange any two indices, sign changes. So, I j k and j I k give you opposite signs. Both of them are present, and therefore, whatever you get out of one term is cancelled by what you get out of the other term. So, again it is equal to 0. So, we have proved that curl of gradient of phi is 0, divergence of curl is 0. Now, what we will prove next time is, what we will develop next time is a technique for doing things like divergence of A cross B or curl of E. These are going to be very, very important when we get to the next stage in electromagnetics. It is even important for proving this very simple fact about magnetic energy, and it is only because we have not developed these techniques that I have been just talking instead of deriving. Using this simple structure, we can in fact make all the vector calculus calculations trivial, and if you know it, you do not need to memorize any of the formulas at the end of your book. Your book has all sorts of formulas for getting the divergence, the curl, then vector identities. None of them are required. We have already figured out how to get many of these results. The remaining results will come out of using this epsilon ijk concept. So, I will complete that next time.